Hello, my name is Michael Schultz, and I've been working with educational modules of skeletal muscle, specifically to meet the next generation science standards at the middle school and high school level. And so we've tried to incorporate some active modeling and more of an engineering and math aspect to go along with the biology of the skeletal muscle. And so we've split the modules into two different levels, one at the middle school level and one at the high school level, with differing levels to meet the different requirements at the middle school and high school levels. And so beginning at the middle school level, we could show an image such as the following. Which begins at the entire muscle and goes down all the way to the single cell and then the myofibril. And then within that is actually the contractile element of the muscle, also known as the sarcomere. And so looking at the sarcomere, we can see a distinct banding pattern, which was discovered years ago by different research teams. And in order to discover this, they used a tool called cross-sectioning. And so if we were to look at the following image, we can see three different red lines. The center line in the cross-section, you can see both actin and myosin, the two components of the sarcomere, one being the thin filament and the other being the thick filament, respectively. If you were to look at the left cross-section line, you see only the thin filament and therefore only actin. And in the right, you see, of course, only the myosin. And so the students could use this information to construct their own 3D models of the sarcomere. And so when looking at the same muscle as in the previous image, but in a more contracted state, you can take the same cross-sections in the same areas, but you will get a distinct and new cross-section pattern. And so the researchers noticed this, and they developed the sliding filament theory of muscle. And so students can also look at these images and try to develop their own theories, their own models of what they think the sarcomere actually looks like in 3 dimensions, to sort of incorporate an engineering aspect and not just look at a 2-dimensional image and learn vocabulary. And so as an example of some modeling by students, this was created by some middle school students at a summer camp, and it's made from different materials all found at Hobby Lobby for relatively cheap prices. And so we have here and here the Z discs, and then the thin filaments are the black pipe cleaners, so the actin, and then the white pipe cleaners represent the myosin, and the pink pipe cleaners between them represent the myosin heads, which bind from the myosin to the actin in order to contract the muscle and create the force required for movement. And then in this case, the student actually used thicker pipe cleaners to represent actin instead of myosin, so they got apparently a little confused, but you can incorporate the thicker and thinner pipe cleaners as well to be more realistic and more accurate in the design of the models. And so these pipe cleaner models are of course 2-dimensional models, whereas the sarcomere is actually a 3-dimensional object within the body itself. And so we've also incorporated a more advanced model that could be done possibly as a project, maybe a final project for the class or something. And it's obviously, as you can see, a little more advanced. It's in the form of a diorama, but it incorporates all of the same aspects as the previous models with the Z discs, the actin, the myosin, and you can incorporate myosin heads as well. And then we have right here a molecule called Titan, which hasn't been previously discussed, but it's a relatively recent discovery. uh, and it anchors the myosin to the Z disc, as shown in the model. And so, I mean, this could be a project, as I said, for the students, a final project, because it's probably going to take a little bit of time to create, but they could get creative with it and use whatever materials they think would work the best. This is by no means end-all be-all product. And so a further step in the middle school module is actually the measuring of force, to incorporate, again, an engineering, a modeling, mathematics, and possibly even a physics aspect to the module. And so we've created a little model here, and it just uses some tongue depressors and Velcro strips, and then a fish scale. And so there's a different number of Velcro strips, and if you were to pull on the model, it will actually measure force. And so you can measure the difference in force between one Velcro strip to up to 5 or even more. And you can use these Velcro strips to represent the myosin heads binding to the actin, so thus creating a different amount of force. And then students could graph the force created by these myosin heads and discover, is it linear? Do 2 myosin heads binding create twice the force of one, or is it something more advanced than that? And so as a final piece to the middle school module, you can actually, if your school is equipped with microscopes, either order slides of muscle or possibly even go to the store and buy something like steak and cut it very thin and mount it on the slides. And so you could look at this muscle underneath the microscope, and you can actually see, possibly at 40 times, or even if you have 100 times zoom, you can see the banding pattern as shown in the previous images on the muscle itself. And so it incorporates more of a real-life aspect to the module. At the high school level, for the high school module, we wanted to incorporate more real-world aspects and make it very interactive for the students to not only learn about muscle and muscular disease, but also prepare them for possible future scientific careers. And so we created a class situation, a class problem, where there's a hypothetical student in the class who has muscular dystrophy and is basically using the class as a support group. And so the class would be split up into various groups, and they would perform different tasks, such as a literature search to learn more about the disease, creating a presentation about the disease and its different aspects, and then possibly even modeling the disease. And so, as you can see in the following image, muscular dystrophy, especially Duchenne's muscular dystrophy, which is the most common, is caused by improper anchoring of the sarcomere itself to the cell membrane. And so this is particularly important in the molecule dystrophin, which can, when it's damaged, such as in muscular dystrophy, can cause the membrane to be leaky and cause the sarcomere not to bind correctly to the membrane. And so students would learn this and look into how this might be caused, what problems it might create for someone with muscular dystrophy, and then also look into how they could model this in its different aspects. And so in a modeling aspect, the high school students could again go back and complete different aspects or all of the middle school modules, especially paying close attention to the force measurements, as force is a fairly big concept in muscular dystrophy. And so they could also then create their own models of muscular dystrophy, as we've created for the modules. And so in this case, we have more of a normal cell, and the rubber bands represent the dystrophin molecule binding the sarcomere to the cell membrane. And in this case, the membrane and the sarcomere are bound tightly. It creates a decent amount of force and is unlikely to break or cause any problems. But in the cell with muscular dystrophy, you can see that the rubber bands or the dystrophin is damaged, so it's much smaller, much weaker, easy to break, and therefore creates less force. And this can show some of the different aspects associated with muscular dystrophy. And again, like in the middle school module, we want to encourage creativity and allow the students to create whatever model they feel fits the disease the best. Again, like at the middle school level with their module, we can use different microscopy techniques to look at muscle under the microscope in exactly the same way, either ordering your own slides or creating slides from muscle found at the store, again like in a steak. And then we also, for the high school module, wanted to incorporate an engineering and a technological aspect. And so what we found was that there is a very cool and very easy to use program called Sketchup, which is owned by Google, and it's completely free, found online. And it's a modeling program that allows you to create your own three-dimensional models and move them around in space. And one of the nice things about it being through Google is that there is an entire database of different shapes, different objects that you can download directly into your computer, and it keeps you from having to create your own shapes. And so I've created a three-dimensional model of the sarcomere, as you can see here. And because of the database, I could even upload this to their database, and then you could download it to your own computer for the class. And so again, SketchUp is very easy to use, and it's pretty fun, quick to learn, so the students could have some fun with it and while still learning and creating their models of the sarcomere, which again are able to be moved in three-dimensional space, rotated, seen from different angles, etc. And so to further the module, we also have a muscle group here at the University of Kentucky, and many of them are willing to answer questions or even Skype into classrooms and answer students' questions, both about muscle, their research, and even about future careers if the students were interested. And so we have a list at the end of the video of the different members of the group and their contact information if you were interested in them getting involved. And so we've also worked with a small company called Backyard Brains that's created different technology that we believe could be used in the classroom. And so one piece of equipment that they have is a small piece of equipment that records EMG activity. And it can be bought either already put together or in separate parts and put together by the students for relatively cheap. And this EMG can record either isometric or isotonic contractions of the muscle. And all of this can be seen in the video from the link at the end of this video. And we also have found a pretty cool YouTube video which we believe will get the students either at the middle school or high school level or even both pretty interested in muscle, and will get them more involved from the get-go. It's called Muscle Man. It can be found at the following link on YouTube.